introduce Matteo. Matteo did his bachelor's and his master's in Pisa. Then he did his PhD at Utrecht and did an Argelander Fellowship at the University of Bonn with Norbert Langer. Then he moved to Santa Barbara from 2011 to 2016, where he was first a postdoc and then a specialist in theoretical astrophysics. After that, he went to the Flatiron Institute in New York City as an associate research scientist, and then became a research scientist there, I think this year. And also he's a visiting associate researcher at Princeton University from 2017 to now. He has received a number of awards, the Berlatani Prize, the TCAN Research Scilog Fellow, Scilog Award, and he has well over 10,000 citations to his papers. So please, Matteo, you can start.
Yeah, thanks so much, Enrique, for that very kind introduction. And let me share my slides so we can get started. Okay. Yeah, it's a great pleasure. Thanks so much for the invitation. And today I'm going to tell you a little bit about my work and the last 10 years of dwelling in the study of stellar physics. And the title of my talk is The New Era of Stellar Physics. And I'll try to justify why I think, we're moving into a new period in the study of processes that occur in stars and how those affect the universe at large. So I'm going to just make a couple of statements about how stars have a central role in the universe. They can be considered universe building blocks. There's 10 to the 22 of them around, and they drive chemical and dynamical evolution of gas. They're responsible for the formation of compact remnants, including neutron star and stellar mass black holes. So we can now detect the merger of these remnants with gravitational waves, something that obviously is driving a lot of interest in the study of properties of the endpoints of massive stars. These same endpoints sometimes correspond to stellar explosions, and some of these are used as cosmic yardsticks. Not only star that pulsate, but also star that explode can be used to measure distances in the universe. So there's a huge importance for cosmological reasons. Finally, stars host planets. And so if you want to understand your planet, you better understand your star. Not only if you're interested in knowing the radius, for example, but also if you want to understand the habitability of the planet, knowing the level of activity of a star is probably something interesting. So that leads to understanding of convection and magnetism in stars. As I mentioned, for galaxy understanding the evolution of gas in galaxies and the ionization of the gas, the stellar feedback is of primary importance. The chemical evolution as well is driven by the evolution of stars. And finally, you all have heard this inspiring results from the LIGO-Virgo collaboration that keep coming in, and we're getting a better and better picture of the properties of the final remnants of massive stars, and we're observing many merger of black holes and neutron stars and combination thereof. Some of the properties of these mergers are unexpected, which is also driving a lot of people like me back to the blackboard, trying to understand what's going on with massive stars. Anyway, so for this talk, I thought that my job could be giving you a little bit of an overview of how we model stars, what are the limitations and what are the advancements that we've been making. Especially, I want to justify why this is a new era of stellar physics. And finally, I'll discuss some problems on the frontier in stellar physics that I've been working on and I think are of particular interest, and then connect, I believe, to some of or many actually of topics in stellar astrophysics, also in ion energy. And it has to do with the study of rotation and magnetism in stars and how this affect, for example, the final compact remnants properties. And if I have time, I'll also touch a little bit on massive stars, which you might know are the less understood stars of them all. Okay, I just want to say quickly, I know you all know this stuff, but it's always good to bring it back. What is a star? Let me close the windows a little noisy. So what is a star? Star is a hot ball, self-gravitating hot ball of plasma. It's important to recognize that for the large majority of the time stars live, its plasma at any point of the star is in a hydrostatic equilibrium, meaning that the two major forces that are at play in the vertical direction, the acceleration mean gravity and the gradient in pressure, are balanced. So when I talk about stellar life, I obviously talk about long time scales. You know that stars like the sun live for about 10 billion years. More massive stars only live for a few million years because they burn their fuel much faster. They're very, very luminous. But what are the relevant timescales that we need to resolve if we want to study massive stars? So the first and the shortest timescale that we want to deal with is dynamical timescale. This is the timescale that corresponds to a perturbation of the hydrostatic equilibrium balance that I was talking about. So if you think about the acceleration, gravity, and gradient pressure, which when they're not in balance, things will move around in the star. In fact, like a pressure wave will be excited, which is a sound wave if you want. And the timescale that this perturbation propagates through the star, which is really the sound crossing time, if you want, of the star, is actually fairly fast. The timescale in this case is the order of less than days. In fact, for the sun, this timescale is about 30 minutes. This is a typical timescale of perturbation of hydrostatic equilibrium. And if you're studying convection and things like that, this is kind of the timescale you want to resolve. The other important time scale is the fact that corresponds to the fact that the star is usually in thermal equilibrium, and the thermal equilibrium is reached on a fairly longer time scale than the dynamical time scale. You can imagine the star being constantly supplied by extra energy by nuclear fusion in the core, but let's assume for a second that we're shut off this nuclear fusion in the core. Then the luminosity of the star is actually completely taps completely into the change in internal energy of the star itself. So the star will start losing its internal thermal energy into photons propagating outward in the universe, and some neutrinos as well, but mostly photons if it's on the main sequence, for example. And so the typical timescale of these occur is the internal energy divided by the luminosity of the star. That's the rate at which energy is lost. And so you can get from the Weyl theorem that the fact that the internal energy is about half of the gravitational energy, and this gives you a well-known Kelvin-Helmholtz timescale. This timescale is about 30 million years in the sun, so it's much longer than the dynamical timescale, but it's also much shorter than the nuclear timescale, which, as I mentioned earlier, is of the order of 10 to the 10 years for the sun. This is the time that the star can remain in thermal equilibrium, and it's pretty much provided this energy, extra energy supply, constant supply, by turning direct conversion of a small fraction of the rest mass of the reacting nuclei for the sun on the main sequence, this is hydrogen, into energy. So this is the important hierarchy in stellar physics. We have a nuclear timescale, which is much longer than the Kelvin-Helmholtz thermal timescale, which is much longer than dynamical timescale. And the hierarchy for the sun, for example, is about 10 to the 15 order of magnitude. 15 orders of magnitude. So 10 to the 15 between the nuclear timescale and the dynamical timescale. That's a pretty large hierarchy if you want to cover it. So that's bringing me to the point I want to make, which is modeling stars. How do we do this? So to model stars, one might imagine that maybe the best way to go about this is just like throw a lot of computational resources to the problem and just say, okay, we just put a star in a box and then we run a large computer simulation, put in all the physics that you want in it and trying to see what comes out. So let's see how that will work. The important thing when you do a numerical simulation is that you want to capture all the scales of the problem that are relevant. So from the smaller to the largest scale. So the largest scale, obviously, in a star will be the, something comparable to the size of the radius of the star. And then the smallest scale, it's probably where the viscosity, so if you think about the Kolmogorov cascade of turbulence, it's where the viscosity stat takes over and then turbulence dissipates. Now, if you assume a Kolmogorov spectrum of turbulence, the ratio between the largest scale and the smallest scale depends on the Reynolds number. So it depends on how turbulent your flow is. And it's kind of like a Reynolds number to the power of 3/4. Now, the Reynolds number in the sun is a very large number. It's around 10 to the 10th, which means that the ratio between the largest and smallest scale is something like 10 to the 7th. Now, this is a big number, and means that you have to resolve very, very small features into your simulation if you want to be completely resolving the turbulence and all the physical processes at work. What that implies if you want to simulate this? Well, it implies that you will have to put the star in a box with a grid of about L max or L min cube, 10 to the 22 grid points. Now, this is a very large number of grid points, but it was required to model a cubic region from the largest eddies down to the viscous damping scale, what is called a direct numerical simulation. Can we do this? Okay, let's look at the fastest supercomputer on Earth. Currently, the Fugaku supercomputer at the Riken Center is like 7.6 million cores. And computer of this scale, petaflop scales, we can run simulation with about 10 to the 11, 10 to the 12 grid cells. And this is something like 10 to the 11 away from what we want. So that's still much different than what we want to achieve to simulate a star in a DNS, direct numerical simulation. But you can say, well, you know, like there is this thing called the Moore's law, and we know that computational power doubles every 1.5 years. And this law, you know, people are talking about the fact that maybe it's about to break. I'm not gonna touch on that. Let's assume for a second that this law will continue being relevant for this type of consideration in computing hardware, and that will continue doubling the power of computers every 1.5 months. And before we look at the consequences of this law for the future of simulations of stars in three-dimensional calculation, let me give you a little bit of an explanation of this plot, which is showing the evolution through the last few decades of the computational powers as measure of, for example, number of transistors inside your computer. And you can see that that number is really scaling with this power law with the 1.5 doubling time, 1.5 years doubling time. But also you can see that the frequency of your processor inside your computer has flattened. It hasn't really changed in the last 20 years or so. You're probably running something with 3 gigahertz, so something like that. And what is really compensating for this flattening of the clock frequency is the number of logical cores that companies are now packing into your CPUs. And your laptop today is more likely to have several cores than it used to 10 years ago or 20 years ago, when pretty much everybody was running with one core. Anyway, this is interesting to think about how things are scaling up and how the technology is moving, trying to compensate this and keep up with this Moore's law. Okay, so if we double up our computational power to every year, every 1.5 years, and then if you want to get 10 to the 11 in terms of improvement, it's going to take you 55 years. So that's how long it's going to take before we're going to be able to run the sun in a box from the scale of eddies down to the scale of viscous damping. Now, of course, as I mentioned before, and you might imagine that this is much worse. It's much worse than that, because that's a time to run, you know, a few turnover time scale of the convection, few dynamical time scale. But as I mentioned, there's a 10 to the 15 time steps to simulate the full evolution, or a little less if you want to simulate the Kelvin-Helmholtz time scale. So if you put that in consideration, it's going to take 55 years to get the dynamical time scale, and then 30 or more, 50 or more years to get to the thermal time scale, and the full evolution of the sun, assuming Moore's law will be the same for the foreseeable future, is going to take more than 100 years from now. So that's a little bit the sad news about fully resolved numerical simulation of stars, and it's also The good news is that models are still useful. It's still possible to run numerical calculations that are incompletely resolving your cascade. So usually what you do, you resolve only some hierarchy going from large scale, and you break the cascade to some point. And we believe that in hydrodynamics, some of the results that we're seeing in this simulation are still robust enough, or at least useful to understand the real astrophysical situation and get intuition about the relevant physics. It might be harder and more dangerous to make extrapolation when you have magnetic fields, so an MHD calculation. The reason being that in MHD calculation, this very small scale sometimes talk to large scale. This is what we call an inverse cascade. Dynamo processes that occur maybe at very small scale in your simulation that maybe you're not resolving might start connecting and creating larger scale fields, which then couple to the plasma and then affects the larger scales. This is obviously, as you imagine, a power spectrum is carrying momentum or energy, if you want, from smaller scale to larger scales, which is opposite of what usually the typical Kolmogorov cascade in hydrodynamics does, where the energy only flows down through the power spectrum. That's why it's called an inverse cascade. So particular attention, yeah, please.
So just, I mean, maybe you'll touch this in a bit, but in your previous slide, so we have to wait 55 years for the dynamical timescale. But what about including mesh that increases logarithmically or AMR? Do you think it's still 55 years from now?
Yeah, so those techniques can help, but like if you think about the sun, the whole envelope is turbulent and convective, and the density doesn't change that much. So those MR techniques are probably very useful if you're simulating something like I don't know, star formation, where you have a huge range of densities, and maybe you want to pack more resolution only where there is action. And these techniques have been very successful in cosmological simulation. For a star, you can gain some time by, for example, packing more resolution just in certain regions. We've been doing things like that, for example, in this modeling of massive stars, where we have thinner convective regions close to the surface, and that's where you want to pack more of your computational power. But you get a factor of a few. You don't get a factor of 100 or so. So yeah, take those time scale as a with a grain of salt in terms of exactly when this is going to happen. But yeah, this is a pretty unavoidable situation for now. Now, something that I haven't said is that this is assuming that we're using the same computational methods, and this is maybe a little bit where you're going. There might be some breakthrough in the future where we'll start using maybe different algorithms to solve some of these equations. In this particular case, Navier-Stokes equation. And that might lead to huge computational improvement that might totally defy this perspective. And honestly, it would be great. The problem is that we don't have anything right now.
Okay, thanks.
That was a good question, though. Okay, cool. So, so we're still stuck on 1D style evolution, meaning that a lot of the time when you hear people saying we studied the evolution of a star down to core collapse, what they've done is that they use 1D model. And 1D model is still the workhorse for the study of stars on the long time scale that we talked about. And I'm not going to tell you too much about 1D, but as you can imagine, the assumption is that although a star is a spherical object, through the time steps that stellar evolution model take, which tend to be long, the properties on horizontal surfaces, which are average along constant pressure region of a star, contain constant pressure, density, omega, and composition. And so these allow to retain a 1D array simplification for the star and to approximate more complex physics using simplified diffusion models. And these models come from theory or even multidimensional simulations and are calibrated via observation. And again, another thing that, it's down to simplify the problem is that microphysics, things like the equation of state, the interaction with heat, radiation, and the matter and nuclear reaction are implemented usually as tabulated properties or analytical fits that to experiment or more modern calculation that come. So these are not calculated in real time using the full-blown physics that process would require in the calculation. So these allow to run a star for billions of years. But of course, this type of model will need to be understood as very large simplification of the real problem. And as I'll mention, moving ahead, in the era of high precision stellar physics, now we're in the place where we can test some of this assumption and see that in most cases, we're not doing a perfect job. Sometimes we're not even doing a good job. And that's where the progress is happening. So exciting times for stellar physics. You probably heard there are a lot of missions and observatories coming online that are gonna pushing the envelope of our understanding of stars. On one hand, there are transient surveys that are unraveling a variety of explosive stellar death that was not predicted. We definitely don't understand supernova progenitors, and there's going to be more coming. Things like the Vera Rubin observatories formerly called LSST, are going to provide millions of transients per night, and some of these are going to be stellar transients, and we'll have to understand what's going on from a big data perspective. And so theory is going to have to catch up. Also, in terms of getting very precise measurement of properties of like luminosity of a star and the fluctuation in the luminosity itself, we're getting exquisite data from telescopes like Gaia and TESS. We had incredible results from Kepler and K2 Bright, and in future we'll have Plato. All these missions are allowing to study the propagation of waves in stars, so through astroseismology, something I'm going to talk a little bit about later. And the astroseismology is really allowing us to perk inside the stars and getting better understanding of our models and also understanding that our theories lagging behind. Finally, the dawn of gravitational wave astronomy is on us. LIGO Virgo finally observing many merger of compact remnants. And potentially we might be able to probe the epoch of reionization and the first stars, hopefully soon with some missions like JWST and HEDGES. And so definitely a lot is happening in the field of stellar physics. And so the thing I really care, and this is maybe the modus operandi and the methodology that I've been utilizing, and I think the community is moving toward, is this idea of having this constant loop between one-dimensional calculation, three-dimensional calculations, and this data, high precision, large data set coming now from space mostly, but not only. And so the idea is that the three-dimensional calculation and theory inform some of this mechanism that we can implement in one-dimensional calculations. Then we can finally test with precision with data that before we didn't have, and so we can iterate. If we find some agreement that we take on board these changes. If instead we find disagreement, that we have to go back and understand what we miss, what is missing in our more sophisticated calculations. Okay, so I want to move into frontier questions, and I'm going to talk a little bit about internal rotation and magnetism. So as you know, stars are born rotating. Most stars rotate with different periods. The sun is currently rotating with a period of about 30 days. More massive stars rotate with periods of a few days, which correspond to rotational velocities at the equator of order of a few hundred kilometers per second. Sometimes some of the stars have velocities that bring the equator close to breakup. So that can be a very important effect. In general, what is not known is the rotation rate of a star inside the star. So we know usually we can measure the rotation rate at the surface, but we don't know what the rotational rate is throughout the stellar structure. And the reason is that it's very hard to probe stellar interiors. Sir Arthur Eddington in 1926 famously stated that would be almost impossible. It would seem that the interior of the sun and stars is less accessible to scientific investigation than any other region of the universe, which seems to prevent the possibility of measuring some of these important properties of stars that link to their final endpoints, like superluminous supernova, GRBs, and things like that. It turns out that he was wrong. This is thanks to the advent of astroseismology. So astroseismology is the study of waves and waves propagation in stars. And in this animation provided by Rich Townsend, you can see a highly amplified version of a pulsating star. And the important aspect here is that when a wave that is propagating throughout the star reaches the surface, is compressed and rarified the gas in different places. And hotter gas is more luminous, and colder gas is cooler, which means that when you integrate the star, even if the star is a point source and you see it from far away, you can still see the fluctuation in brightness as a function of time, which create what is called light curve. And if you take a Fourier transform of this light curve, you can identify the modes of oscillation at certain frequencies. And this gives you some information about the musical instrument. This is really a three-dimensional musical instrument where the oscillation are three-dimensional. And as they propagate through the star, they tell something, the properties tell something about the structure of the instrument. And that's what astroseismologists try to decode and learn. Now, the question is, obviously, a star is a musical instrument, but musical instruments do not play unless someone puts some energy into it. You have a guitar there. If you don't strum it, it's not going to play. Same for the sun. If there's no energy injected somehow, it's not going to start oscillating. Turns out the sun is oscillating. It's called stochastically excited oscillation, or Sol-like oscillations, because the first time we saw it was in the sun, but many stars do oscillate in that way. And what is really playing the instrument is actually the turbulence that associated with convective motions. So you know that actually turbulence and turbulent convection excite some level of noise, so some acoustic waves. If you try boiling water to make your pasta, as I'm sure you do, in the kitchen, if you leave the kitchen, you can tell when the water is boiling just hearing the sound. And so the only difference with that actually is that in the sun, the convective cells are much bigger. They're the size of Mexico, and so that provide large amount of energy that you can actually use to resonate the whole star. So this was observed in the sun, and before the advent of space astroseismology, space photometry, this was the situation. Only a few stars were observed to oscillate the same way as the sun through these stochastically excited modes. But then, after Kepler came online, thousands and thousands of stars on the main sequence, and particularly on the red giant branch, were observed to actually show this Sol-like oscillation. The reason why we needed to go to space is because you can see from this plot, which is an HR diagram with some tracks for stuff between 1 solar mass and 2.5 solar masses, and overlap are all these data points coming from Kepler showing the amplitude of the Sol-like oscillation in the relevant stars. You can see stars of the typical star in the Kepler sample was something like 1.5 solar masses or so, and the amplitude of this pulsation is very, very small. It's part per million, up to a part per few thousand up here. So this is actually a very tiny level of variability, which is impossible to capture from the ground because of the atmosphere. And so you need to go to space to be able to do this. And Kepler is observing stars for a long time, looking for planets, but in that time is also capturing all this variability from the star. And that's where astroseismology was allowed. Okay, so I'm gonna show the only technical plot that I'm gonna show in this talk, and this is called a propagation diagram, and it's really the tool that astroseismologists use to understand the musical instrument, the star in this case, and understand how these waves that we observe at the surface propagate. So before I say that, I want to just go back. Actually, I forgot to say that stars like the sun, they burn hydrogen on the main sequence. And then when hydrogen is exhausted, the core contracts and the envelope expands and the star becomes a red giant. And this is what all the stars here we're looking at are red giants. On the red giant branch of different radii, star goes from a few to tens to 100 solar radii, so they get very big. And of course, as they get bigger, they oscillate with larger amplitude. Also, the frequency of the oscillation goes down because the musical instrument gets bigger. So, it's like going from a violin down here to a cello up here. And you can tell straight away by looking at the frequency and the amplitude. In a sense, you can tell what kind of star you're looking at. But you can tell more, as I will show you in a second. The important thing to remember is that along this branch, the core is contracting, the envelope is expanding. Okay, so let's look at the structure of these stars on the red giant branch. This is a plot, as I said, it's a propagation diagram. We have the radius, logarithm or radius on the x-axis, and then we have characteristic frequencies on the y-axis. These are in microhertz, and microhertz are very small, meaning that the periodicity associated with the fluctuation that we talk about are going to be very long. So in fact, it turns out that these stars oscillate with periods of weeks to months. So these are very, very low frequency sounds because the musical instrument, again, is that big. The two lines I'm showing here are two characteristic frequencies that are particular to the star. The blue line is called the Lamb frequencies, and is nothing else, as you can see here, as something like proportional to the inverse of the sound crossing time. So it's the time it takes for sound waves to propagate. It's the inverse of the time that it takes for sound waves to propagate through the star. So it's related to the free-fall timescale, if you want. It turns out that acoustic waves, so sound waves, can only propagate in a cavity where their frequency is higher than both the blue line and the red line, which I'm going to tell you in a second what it is. So if I excite a sound wave at 1000 microhertz, you only get down into the star at about 0.01 radii and then come back. So you oscillate in this part of the instrument. The G mode cavity instead, and this is called the P mode cavity, P mode because the restoring force is the gradient pressure. The red line instead is the square of the Bruns-Väisälä frequency. The Bruns-Väisälä frequency is the buoyancy frequency. So in a stably stratified part of the plasma of the star, if you take a piece of plasma and you just push it down, that piece of plasma wants to go back to the equilibrium point and will go back and oscillate a little bit. Similar to if you put like a beach ball at the surface of the ocean, you just push it down, it will go back and forth a little bit. That's the buoyancy frequency, or the Bruns-Väisälä. It turns out that that's the frequency, the frequency of gravity waves, which are waves where the restoring force is buoyancy gravity, can only propagate below the red line and the blue line. Why am I telling you all this? Because this naturally divides the star in two large cavities, the P mode and the G mode cavity. It turns out that for this increasingly getting bigger stars, these red giants, the P modes are excited, as I mentioned, by the turbulent convection which is occurring in the envelope of the star. And this P mode propagates down to the Lamb frequency and come back. However, as you know from quantum mechanics, some of this wave energy can actually tunnel through this evanescent region between the Lamb and the Brunt, and a tiny bit of energy is actually dropped into the G mode cavity, which, as you can imagine, is in the core of the star, the contracting core of the star. So it's all made of helium down here, and a little bit of iron too, but mostly helium. And so this G mode cavity can get excited as well. So in a sense, the P mode can slowly start playing the G mode into the core. And what happens is that you form this eigenfunction. So this is a unique standard mode, which is made of three parts: the P mode, a little evanescent region, and the G mode. Now, why am I telling you all this? Because if you see one of these things called mixed modes, because they have both P and G nature, at the surface of a star, you actually probing both the envelope and the core. And if you find different mixed modes which have more inertia, meaning that more of the mode is propagating in the envelope or more in the core, and you have one that is more P-like and one is more G-like, you can get like you can get a measure of the core properties and the envelope property in differential way. So you can have the possibility to probe the differentially envelope and core of the star. So if you look at something like the splitting of the mode, and the splitting can occur if you have one of these waves propagating a region which is rotating. So you can have modes that start being splitted by the fact that there's rotation. If you measure the amount of splitting in a P mode dominated mixed modes, that will tell you mostly about the rotation rate in the envelope. But if you measure the splitting in a G dominated mixed mode, that will tell you something about the rotation rate of the core. So using this trick, people started finding that the core of the stars, as they move on the red giant, is rotating faster than the envelope by a factor of 10. In a sense, the faster than the envelope thing was predicted. As you know, as you're contracting, the ballerina effect, you expect things to spin faster, and you're expanding, you expect things to spin slower. But the interesting thing, and this plot here showing as function of radius as for star climbing the red giant branch. So these are stars that are leaving the main sequence and now they're expanding. This is the surface rotation, radius. And this is the rotation period of the core. So I want you to focus only on this group of stars, the early RGB, hydrogen-bearing stars. So these are stars that are climbing up the RGB. And you can see the interesting thing is that the core rotation, yes, is faster. It's faster than the envelope, but actually what you're seeing is that it's not spinning down. It's actually staying constant, or actually, it's not spinning up. It's actually spinning down a little bit. You can see each cross is a star, and the period of rotation is 10 days, and it's actually slightly increasing as the radius increases. This is unexpected because as the core is contracting, you will expect things to spin up unless there is coupling between the core and the envelope. So there's angular momentum transport. Obviously, this idea was already discussed and theoretically implemented in stellar evolution codes. People had thought, oh, there could be all these classes of instabilities and circulation and torques that can lead to transport of angular momentum, coupling between core and envelope. You can imagine like shear, mixing, circulation, rotationally induced circulation like Addington-Sweet line circulation, magnetic torque. If you have a magnetic field in both the radial and horizontal direction, you can exert the torque. You can also have internal gravity waves themselves propagating angular momentum. And it's possible to treat these in 1D code because of the assumption of shallow rotation I mentioned earlier on. So I went on, and back in 2014, we tested the theory, we tested the models, and we ran models of stars using MESA, which is a stellar evolution instrument code. And the black line here is showing for a model the period of rotation of the surface, nothing special here. The star is expanding, and so the surface is spinning down. But then the other colored lines are the expectation for the core rotation as the star is going up the red giant branch, as function of the different assumption for angular momentum transport. So the green line is what you expect if there was no angular momentum transport. So pure conservation of angular momentum, ballerina effect, things spins up substantially. And you end up with rotation rate of a few hours, so very fast rotation. And the purple line is that if you include meridional circulation and shear, can couple a little bit, but not much. And then the red line was the state of the art in terms of maximum coupling. And that was the so-called Taylor-Sprout dynamo. This is the magnetic torque type of coupling. And when we overplot the data, this is what we found. Definitely the model cannot reproduce the trend and the values observed for the core rotation of the red giant. We have way more data now, and this trend is confirmed. And so it seemed clear that we didn't understand angular momentum transport in these low mass stars. So there was a little bit of a push to go back to the black hole. It was done, and one of the outcomes was that the group led from Jim Fuller came up with a revised version of the Taylor-Swift dynamo, where they look at the saturation mechanism, and they came up with a different way to saturate the magnetic field, which led to a much better agreement with the observation. So this magnetic torque lead to larger coupling, and you can actually reproduce the observed core rotation both on RGB and on the clump. The clump is when the star is actually burning helium in the core. And then also for the white dwarf observation, so it seems like the full history of rotation rate can be simulated this way. Obviously, there's still work to do, but this is encouraging. This allows also to make prediction. If you port this understanding from low mass stars and assume the same physics is occurring in massive stars, this allows Jim Fuller and Ma to study the final Kerr parameter of a black hole that might merge in the LIGO band, and they found that the expected Kerr parameter is very small, always of order of 0 or a little larger, which tentatively in agreement with some part of the data, but not all the data from LIGO. And I think the recent LIGO papers from a few weeks ago show that actually there's even more tension now. This might have to do with different, I think this is some of the LIGO data. It's not the most recent release, but you can see that there's definitely mergers that show level of chi effective, which is a measure of the projected and weighted Kerr parameters for the black holes in the merger system. And it's possible that there are other ways to maybe make binary black holes that through different channels than the classical channel coming from a single star or binary stars. And so there's recently I've been working on evolution of star in active galactic nuclei. I don't have time to talk about that today, or even star mergers. But yeah. Okay. Yes. Good time here to stop and get question on this first part.
Yes. So I think the stars you mentioned in your previous plots were somewhere around 2 solar masses, and then you suddenly jumped with those conclusions you had there to the massive stars where you have very different time scales. So I'm not sure if the alpha n time scales will translate proportionally, or what's happening there. Why can't you extrapolate those results from those low mass stars to the larger ones?
Yeah, it's a good point, and I didn't really went at length talking about this. It's a leap of faith, yes, and I'll spend a couple of words why maybe it's not too bad. But first, let me tell you why we do that. We don't have data for massive stars yet. Astroseismology is definitely a field that has blossomed in the study of low mass stars, where we have a lot of data coming from Kepler. There is also it's much harder also to do astroseismology in more massive stars, and there's probably more happening there in terms of wave propagation and other perturbations. In terms of the physics that we're learning, though, I think that some of the physics is going to be solid and can be ported. The plasma conditions are not very different. Yes, massive stars tend to be hotter, and the structure will change, but most of the things we're learning here is about relative regions, and so I think that it would be very weird if things really not work very differently in massive stars. The time scales are different, it's true, but in the models that we run, we do take care of that, because things like the implementation of Taylor-Swift dynamo in a 1D code, is coupled with the stellar evolution. And so, for example, that massive star will have less time to lose angular momentum than like a red giant star who lives in like millions of years just on the RGB. When massive stars move from the main sequence to the red supergiants very rapidly on the Kelvin-Helmholtz timescale. It turns out that many of these processes, like the Taylor-Swift dynamo, is kind of self-regulating. I'm kind of trying to explain it a little bit in a simple manner, but as you contract your core and the envelope expand, which is a typical thing that happens for these massive stars as well, as you become red supergiants, as I mentioned, you create some amount of shear. That shear will take any magnetic field and wind it around. So that field will be amplified in the toroidal direction until it becomes unstable to what is called the Taylor instability. And then that Taylor instability produces some level of poloidal field. At the point you're in business, you create a dynamo loop, you have a B phi and BP, you have a torque proportional to the product of the two, and you couple to the stellar structure. And the interesting thing is that if the star is evolving rapidly, we'll create more differential rotation. And at the same time, because of that, we'll create a stronger magnetic field. So in a sense, this process kind of feed back to each other, and it can compensate. If you have a shorter time scale, you have larger fields and more torques. So it kind of, there's a little bit of a compensation effect happening, self-regulation if you want. But yes, and this is kind of included in the models. But you're right, it could be that maybe massive stars have other processes that are relevant, or maybe for some reason this process works differently. And that's something we'll have to try to test and study in the future. And hopefully we'll get good data for angular momentum transport also in more massive stars. Probably will be very hard to do it for the progenitor of black holes, but maybe we can get closer. So like start doing in stars like 6 or 7 solar masses, maybe even 20 at some point. We'll see. But that's in the making.
Right. So if I get your point correctly, then you're saying that these results where they predict that the progenitors for the gravitational wave mergers should be slowly spinning.
That's correct. So if you have a single star,
right.
Most of the single stars you can see here, they produce like Kerr parameters of less than 0.1, much less than 0.1. So I think it's ordered 0.01.
Right.
Mm-hmm.
What I was looking at a little while ago is this 2016 or 17 paper where you have, I forget the first author, might be Liu or something like that, but you have Meder and I think you have Calogera, and they're trying to show that if you turn on Taylor-Sprout, if you turn it off, I'm sorry, then you can produce the fast spins in high mass X-ray binaries. Yeah. But I think that assumption of turning off Taylor-Sprout is quite drastic from all these experiments that you're showing and all these observations. I mean, numerical studies, of course, right? But also the observations. So
yeah, I think I'm pretty convinced by now, after being working on this, that stars do transport angular momentum very efficiently in general. So if you see a Kerr parameter, large Kerr parameter in a merging compact remnant, or even in your, when you see a rapid rotating pulsar, that this is recycled. So something has happened there after stars. But I believe that most stars, and there might be some very, very particular exception, so for example, progenitor of long GRBs, which might have gone through some interesting evolution, like chemical homogeneous evolution. But if the massive star expands, go through the red supergiant phase, then there's no way out, I think, there's no way out, and at the end you're going to have very small Kerr parameter. So if LIGO tells you you see large Kerr parameters, then that's going to be some kind of exotic evolution where either you had some binary interactions of sort, or maybe it was a dynamical process, either in AGN or clusters, or maybe some kind of chemical homogeneous evolution. Although the chemical homogeneous evolution panel gives you always this interesting properties of aligned spins very rapid in both components. That doesn't seem to be the case of what is observed in life. But more work needs to be done. Yeah.
Okay, thanks.
No, so now I'm confused. So,
go ahead. Yeah, I like this.
So isn't it more expected since high mass stars, the grand majority are in binary systems, we would expect for the Kerr parameter to be large, not small.
You can see here, like from Jim ran also a few stars with a different type of binary interaction. And you can see that does give you a little bit the range of what can be done. Case A and case B doesn't give you much, because by the time that you spin up the star, then you still have enough time for spinning down the core of that object. You can do spin sinks if you use tides, or if you are in the chemical homogeneous scenario. You could also have something called like case C mass transfer, and I think Enrico has worked on this problem a little bit. You can have you can fine tune your accretion rate to happen very late in the evolution of the star, so that the star will not have time to lose angular momentum and so will not spin down. But the parameter space for that is very, very small. Okay. So yeah, so it's true that most massive stars are in binaries, but after they interact in a binary, they also evolve like single stars. So you kind of back on, it's a single star with different initial properties, but you end up being in the same physical wheelhouse, and you have to obey to the same physical law. So it's still going to transport angular momentum through its core to the envelope. And if you lose angular momentum, or you expand, you're down to the same result as the black dot that you can see. Okay. Cool, great. Okay, let me, how much time do I still have?
What, like 10 minutes? 10,
Good.
15?
Okay, so that's enough. I'm going to tell you a bit about magnetism, because I think it's very interesting also to understand a little bit more what's happening in the core of stars in terms of the magnetization, especially if you want to understand what's the final magnetization of compact remnants. People are interested in things like magnetized white dwarfs and magnetized neutron stars, or magnetars. So there's this interesting mystery that was brought to me and Jim a few years ago that still come from astroseismology. So, and it was this. Okay, so let me explain what the puzzle was. As I mentioned, stars on the red giant, they oscillate. They have this stochastically excited oscillation due to turbulent convection in the envelope. And this gives rise to this set of modes at certain frequency. And you can see here I'm showing two almost identical stars. In the HR diagram will be pretty much overlapping. There's two red giants showing this mixed modes oscillations, stochastically excited. And this is the power spectrum. So it's the power density on the y-axis and frequency of the on the x-axis. You can see the spectrum, it's kind of these envelopes of modes, and it peaks at around 220 microhertz. So this is something that's oscillated with periods of days to weeks. So it's like a big instrument. And you can see there's colors showing different peaks that correspond to different oscillation modes. And you can see L equal 1, 0, 1, 2, 3. So this is the harmonic degree of the modes. If you remember, when you divide things in spherical harmonics, L equals 0 is your fundamental, if you want, like the radial mode. L equal 1 is dipolar modes. L equal 2 is quadrupole. L equal 3 is octupole. And you can see that those two stars are interesting in the sense that the power spectrum is almost identical, with the exception that L equal 1 modes are depressed, meaning that L equals 0, L equal 2, L equal 3 seems to have the same amount of power, almost the same amount of power, but the L equal 1 seems to be almost absent in the star, and the other one is normal. It's kind of like the star is playing a symphony, but some chords are missed in one star. What's going on here? So the key piece of understanding that came to us, so how we think we cracked this puzzle, was understanding that the L equal 1 modes the L equals 0, do not talk to the core of the star. And the reason is that something I haven't told you, but the P modes can exist in the radial form, but G modes cannot. So the L equals 0 mode is a purely P mode that doesn't couple to the core, while the L equal 1 mode is one that couples to the core the most, with L equal 2, L equal 3 coupling very, very little amount. And the reason why the L equal 2, L equal 3 couple less is because they have a larger evanescent region. And so in a sense, less and less energy is penetrating in the core. In a sense, this led us to think that what was the difference in these two stars is that was in the core. So in the core of one or two stars, some process was sucking all the energy of the mode of L equal 1 mode. so that at the surface you will see very amount of oscillation. So in a sense, the turbulent convection is exciting the P mode. P mode tunneled through the core into the core, excited the G mode. The G mode somehow is dissipated, and so it doesn't talk back to the P mode. And at the surface, you see a depressed amplitude. So what's going on in the core? Well, as I mentioned, I think the key solution is magnetic fields. So we ideally started thinking that maybe if there was a magnetic field strong enough in the core, that will affect the propagation of the G modes. So, but how that could be? Well, so one possible idea is that if you have a magnetic field line, think about this little string into the core, and then you have a G wave, G mode or gravity waves coming. The gravity waves, as you know, for observing ocean waves, which are a form of gravity wave, displace the liquid or the plasma in this case, mostly horizontally. So as the wave arrives, what it wants to do is to bend the magnetic field line in the horizontal direction. So if you have a vertical field line, it will try to be twisted back and forth by this wave. Now, obviously, this can happen as long as the restoring force of the wave dominate the restoring force of the magnetic field. So as long as the buoyancy is larger than the Lorentz force. But if you increase the magnetic field amplitude, at some point there's going to be a critical magnetic field about which the Lorentz force dominates and the wave is affected. So the propagation of a wave is impeded. So in the presence of a strong magnetic field, the magnetic tension force can become compared to buoyancy. When this happens, you have this critical field strength that can be calculated, and that can lead to the trapping or propagation into alpha or magnetized gravity wave into the core. And this wave tend to dissipate very rapidly. So our working hypothesis was that, and we verified this also with numerical calculation, that the picture is that these P modes tunnel into the core, they turn into gravity waves, but then they encounter this magnetic field. And so these are either turned into magnetogravity waves or reflected and trapped into the core. And it turns out that actually the mechanism that is most likely to happen is this transmission into alpha waves. And these waves are dissipated pretty quickly into the core. And the typical critical magnetic field that you need is 10 to the 5 Gauss, so 100,000 Gauss. Yeah, this is just to show you that we actually run a setup where we tried this idea. We run Daedalus modeling of this, and we show that in generating internal gravity waves in a Cartesian setup, we're able to stop them and to either reflect and dissipate them exactly at the level where the magnetic field reached this critical level. The solution is actually can be reduced by some analytical theory. I'm not going to go into that. What I want to show you is that with this new understanding that maybe when we see a depressed dipole mode star, what you're actually seeing is a star that has a magnetic field in the core in excess of 10 to the 5 Gauss, at least the radial component. And so with that notion in mind, we went back to the data. And so we plotted the data as function of mass. So these plots here are showing the characteristic frequency, which is the peak frequency of the oscillation. And for your interest, the stars actually tend to evolve in this direction. They go from large to lower frequency, again, because stars are becoming bigger instruments as they move up the red giant branch. And the y-axis, the visibility square, which is a measure of power density of the mode. And you can see there's 2 branches. And I want to stress here that each dot is a star. So there's thousands of these stars. And you can see this branch is the normal star up here, constant more or less visibility. And then there's a branch of depressed stars down here, which really separates very well from the normal stars. But most interestingly, if you plot things as function of mass, you see a trend in the fraction of depressed to normal stars. There's basically no depressed stars at masses lower than 1.1 solar masses, and then the fractions start to increase. If you show this in a plot where you plot the fraction of stars with strong internal magnetic fields, so the fraction of depressed stars on the y-axis, and the mass of the object in the x-axis, I know that the masses can be recovered very well because we have astrocosmology measurements and the scaling relation that allow you to get the mass with a precision of about 10%. You can see that the interesting thing is that we only see stars with core magnetic field on the red giant branch for masses about 1.1 solar masses. But this is very interesting because these are the descendant of stars that were radiative in their core for masses lower than 1.1 solar mass on the main sequence and convective above 1.1. The reason is that stars like the sun, they're radiating in the core because they're burning hydrogen via pp chain, but stars about 1.1 solar masses, they start being hot enough in the core that a large fraction of the energy is produced by CNO cycling of hydrogen. And so their gradient temperature is steeper, which leads to convection in the core. So what I think we're seeing here is the imprint of dynamo-generated magnetic field on the main sequence. So this is something that people have studied. The ability of run modeling of this core convection is something we had for years now. And equipartition dynamo at the level of 10 to the 5 Gauss actually routinely found in simulation of stars from 2 solar mass up to tens of solar masses, work from Sascha Braun, for example, and Kyle Augustsson. And magnetic field topology is usually complex, but stable magnetic field configuration can be achieved where at the point of turn off of the convection, you could imagine that some of the magnetic flux can be arranged into structure that are stable. They're not dynamically unstable, which usually require both a poloidal and a toroidal field to be interlocked. And if you conserve the flux, because the core is a little bit contracting later on, you can easily lead to fields of 10 to the 6, 10 to the 7 Gauss on the red giant, which is plenty enough for us to explain this depression of the mixed mode.
Sorry, Matteo.
So, yes. Question.
So I missed how this. So I think I understand the general idea, but I missed why is it affecting L1 and not the other modes?
Yeah, let me show this. Since we spent some time on this, it's good we can use it. Okay, so look at the blue line. Okay, that's the Lamb frequency for L equal 1. Okay, so for L equal 1, if you this is the definition of the Lamb frequency is the lowest. If I put L equal 2, it's multiplied now by 2 times 3, so it's a 6 times higher. Sorry, it compare 1. 1 would be 2, and so there's a factor of 3 in frequency. So this blue line for L equal 2 is moved to the right. Okay.
Okay.
You follow me? So meaning that the distance between the red lines and the blue line for the same frequency of the wave, it's larger. Now you know that a factor of 3 for something that decays exponentially, it's a large factor because you know the wave function here decays exponentially because it is a tunneling process. So what turns out is that L equal 1 is the one that can talk the most to the core, and L equal 2 and L equal 3 increasingly talk less and less. And so if you look at this, at this plot that I was showing earlier with so you can see that the depression in L equal 1 is the largest. The depression in L equal 2 is little smaller, but there is a little bit. You can see here these 2 modes are a little depressed, and L equal 3 they're basically the same. And we look at this more quantitatively, and it kind of matches the predictions. You can predict exactly how much energy is handling through if you have an understanding of which mode you're looking at.
Okay, and in L equals 0, you wouldn't get this same
L equals
problem?
0 doesn't couple to the core because there is no L equals 0 G modes. G modes propagate horizontal. There's no. Okay. They need to have a horizontal component, and L equals 0 doesn't have one. So,
okay, perfect.
Okay.
Great, thanks.
But that was a good question. I didn't have time to to really go through that, but that's the technical aspect. It's an important one. Thanks for asking that question. So, okay, so I'm almost done. Just want to say, okay, so we have these magnetic fields. This magnetic field might be coming from phases of convection that are equipartition. And we kind of proved here, I think, that convective phases of convection that lead to a dynamo can lead to magnetic field that can be transported in later phase of evolution. So this idea of maybe getting equipartition field in certain regions that were convecting a star is an important one. Then, like it's possible that some of this magnetic flux is conserved. So if the magnetic field is not destroyed by other processes, then you can assume that it will lead to some kind of increase in the magnetic field amplitude via magnetic flux conservation, where, if the core is contracting, you could imagine the magnetic field will increase in amplitude with the ratio of the radii squared. And if you do that, if you look at 10 to the 5 Gauss on the red giant, you can actually lead to magnetic fields that are in the ballpark of magnetized white dwarfs, 10 to the 8, 10 to the 9 Gauss. And potentially the same mechanism might be important to determine the magnetic field in some young neutron star and potentially magnetars. So magnetar field level fields are actually possible. This is something that's been discussed in literature, but I think here we're showing a pathway of study using astroseismology to really trace magnetism inside stars across their evolution. So I want to finish with conclusions. We talk mostly about astroseismology, but I think it's useful to think about it as a probe of stellar interiors and a way to understand details about important processes inside stars like rotation, angular momentum transport, and magnetism. I think we learn a lot. We understand that it was a huge amount of coupling between core and envelope in stars, and that most compact objects are likely slowly rotating. It's also important to understand that magnetic fields are potentially ubiquitous in stars above 1.5 solar masses, because these are the stars that have convective cores. These are not included in stellar evolution, so this is something important that we need to rethink. If these fields are ubiquitous and this large, are those important for processes like angular momentum transport again, or maybe mixing? That's something to think about. And yeah, I want to stop here because I think I'm running out of time. And if you want to ask more questions about this, I'll happy to. And if you want to ask me questions about more massive stars, we can go into that maybe during the discussion session.
Muchas gracias, Mateo. No, I'm sorry, I start speaking Spanish. Thank you very much for the talk. Does someone have questions? I think most of the discussion was
well, if no one's asking, then I want to ask then.
Okay.
So
yeah.
You told us all this theoretical point of view, but how do the observations obtain all this asteroseismological data that you can compare to?
How do they take this observation? So yeah. So that's I don't do that with theories, but I know a little bit about it.
Well, you know more than us.
So yeah, so the idea is this: you have a star, and it's oscillating, and the oscillation leads to fluctuations in temperature at the surface, and those fluctuations in temperature turn into fluctuation in luminosity when integrated. Okay, so now you take something and you get something like, you take the light curve and do a Fourier transform, and the Fourier transform of the light curve. Look, so this is a piece of it. Sorry, I should. This one, it's the power spectrum. So this is literally years of data from Kepler, constantly looking at this red giant, and then you get this power spectrum, and so you get these modes, so different frequency. Now, there is a theory that allows you to identify what these modes are, and they actually equispace in frequency here. That's actually a theory predicts it, and the theory, is like allowing you to do something called mode identification. So for the problem here that I discussed so far, that's not too important. What you need to understand here is just understanding that these are mixed modes, and that there is a you understand the angular degree, and then you see that there is a depression. That's all you need in this case. But there's more sophisticated things like what I talk about, splitting to measure the rotation rate. What they do, they will look at, for example, the helical one mode that propagates through the core, and if you look at in detail, you'll find that there is one mode in the center and two to the side, and the distance of these two, it's called delta nu, small delta nu. It's a frequency that can be turned into the rotation rate of the part of the star where the modes spend most of the time. So if you know that this is a P-dominated mode, you will know that this is mostly spending time in the envelope, and usually you expect a small delta nu. If you get a G-dominated mode, let's say this one, that one is living more in the core, and so you see it's actually tend to have a larger delta nu. That's what people have done. And you do this systematically for many modes and many stars, and you find a statistical picture of what this trend in rotation rate is. Then there's more complicated stuff that people can do, which I'm not completely an expert into, but like the most complicated thing you can do is go into the sun and do helioseismology, and then have hundreds of these modes, and the eigenfunctions, that things I showed you before, exactly where the oscillation occur. And because different modes spend more time in different part of the star, it's kind of like you can reconstruct the internal structure of the star doing what is called like a reconstruction of and you look at 100 modes, and it allows you to reconstruct really the profile. I don't know if you've seen this profile of rotation rate in the sun, where you actually can tell the latitudinal differential rotation. That you can do it in the sun because you have so many modes, and also you can resolve the stellar surface. But in that case, it's more complicated. You need some modeling, and not an expert on that. But people are working on these things also for massive stars. There's some cases where now we have multiple modes, and people are starting to do things like 2 zones modeling, where you can maybe measure differential rotation in the core and the envelope of a massive star in the main sequence. So far, what people find is that main sequence massive stars seem to rotate fairly rigidly, and which is consistent with this idea of pretty efficient angular momentum transport as well. Okay. Unfortunately, we don't have measurement past the main sequence, and we will probably never have them, or it'll be very hard for massive stars.
Well, maybe when we can model with our 3D numerical simulations in 200 years.
Yeah, exactly. I think that's more likely at the point.
Okay, thank you.
Thank you. Does someone else have questions?
Yeah, sure. We have lots of questions. We're just being shy.
Oh, okay.
So I found the paper that I was telling you. It's 2019, not 16, and it's by Kim, Marchant, Fraggles, Maynet, and Calogera. So yes, so what's from what I remember from case M, there's not much evidence of that happening still when they do these VLT flames and all these surveys. They haven't found really serious evidence to support case M or fast rotating mixing, stuff like that. So you need probably to use this other thing which Diego was mentioning, which is multiple systems. But what would be your take? What's the most reliable or more consistent mechanism to produce these GRBs, long GRBs?
Yeah, okay. So the question about long GRBs. Yeah, I don't know. It's an open question, I think. GRBs are also this very, it's in the local universe is 1 star in 1,000. Sorry, one in 1,000 supernova. So it's a very exotic type of evolution. So the fact that maybe we haven't seen any star on the main sequence doing this in the LMC, I mean, it's maybe not too surprising. The theory, I mean, some of the theory shows that this kind of like evolution is possible if you go to low enough metallicity, LMC. But also we don't understand mixing, rotational mixing well enough to say, oh, it's going to be LMC or it's going to be SMC or it's going to be lower. So it could well be that that threshold is lower, and there could be other things. Like those GRBs long GRBs are not only found at low metallicity, although there is a trend. There's some that observe at high metallicity. What are those? So it's possible that there may be different channels. They're all exotic, but they're different. Recently, we have this paper, which is also, we started working on this idea of evolution of stars in AGN disks, and that's something, and maybe it's providing some thoughts for other ways to make GRBs. For example, in that work, we have those disks around AGN, so they're very tiny, but they're very dense. They last for millions of years, and it turns out that they're full of stars because the central region captures stars from nearby nuclear clusters. So you can have thousands of stars trapped into these disks. And also, once you have one of the stars, even like one solar mass star trapped in the disk, it grows in mass very rapidly via Bondi accretion. And it turns out that if density is high enough, you make a 100 solar mass star in no time. The rotation rate also, you can, as you're accreting, you also accreting angular momentum, and you can make almost immediately like a rapidly rotating, very massive star. And you can keep it rapidly rotating. So I don't know, we have this paper where we say that this might actually lead to long GRBs embedded into these things. I mean, this is still very, at this, I would say, speculative level now, but with running more models, and this seems to be an interesting potential outcome. The question is obviously, are those long GRB gonna look the same as the one that are not embedded in anything? And there's this paper we wrote with Rosalba Perna, which shows that depending where you are in the AGN disk, you actually can emerge as a normal long GRB, or maybe have a little bit of a muffle long GRB. But so these are things to keep in mind. So what I'm trying to say is that we don't know, and there's a few ideas out there, and I think we're still in a phase where people should think out of the box, because we don't really have a firm, as you mentioned, measurement or observational clue about what the progenitor of these exotic long GRBs are.
Now, for this AGN disk long GRB, there's no association that I know about between long GRBs coming from the central part of spiral or any galaxy. Is there?
Well, there is a paper from, I think, from Fruchter that shows that long GRBs seems to be, I don't know if it was Fimbo or Fruchter 2006, but I think there was they look at, so most of the GRBs are cosmological. So it's very hard to, sometimes you're lucky you find a galaxy, but it's not like you're not seeing, Andromeda and you say, oh, it's here. There's maybe one or two cases where that's been done. But most of the long GRB, if you look at the light of long GRB and light of the galaxy, they seem to be concentrated in the central region. So what that mean? I don't know, but it's something that made me think that maybe this is an interesting avenue. But yes, it could well be that even if these things happen, they're likely subdominant. But maybe potential channel.
All right, thanks.
Of course.
Okay, does someone else have questions?
I think we've lost most of the listeners by now.
Yeah.
Guys, I apologize for being like 5-6 minutes late. I literally messed up with the time. There was actually a funny moment. I was in the other talk and I got like Diego's message. Just like I jumped out, and then I was trying to be very, very like subtle, getting out of the room so that people didn't feel like kind of coordinating here. So I didn't want to. And as I was getting out, I dropped everything, literally my laptop, my stuff, everybody. So the speaker stopped, everybody turned. It was like a very funny moment. So I had to go and explain what happened to when.
All right.
Yeah, don't worry.
Thank you very much for the.
Thank you very much for the talk. Yeah.
Thank you, Matteo.
I will be